Yeah, so let's talk about different kinds of studies. We're going to talk about cohort versus case control studies versus cross-sectional studies. In a cohort study, we follow a group of individuals over time. So what that means, it involves repeated measures collected on an individual. Like my smoking study I'm doing now, I'm following people across 3 time points and collecting data on them at 3 time points. The idea here is to understand if an exposure results in some kind of a disease outcome. Now, in my study, I'm not doing that. So, but you can still do prospective or longitudinal studies. What did I call them here? I called them cohort studies. Cohort studies also have different names. Longitudinal studies. Sometimes they're called panel studies. It means they just have repeated measures. In my case, I'm not looking at exposure on an outcome, although I sort of am because I'm seeing exposure to a treatment. Will that affect something like quitting smoking? So in a sense, that is still a prospective study. But anyway, cohort studies can be 2 different types, at least 2 different types. We either do a prospective or a retrospective cohort study. Prospective means looking forward. Retrospective means looking backwards. And within a prospective, we can have a couple different types as well. One is where we start with exposure. So for instance, I could take smokers and compare them to non-smokers and see which one develops emphysema later down the line. So that would be exposure first. Another one is to allow exposure to develop on its own. And this is most of the research that I've been involved in, where we've tracked adolescents to see which ones start smoking. So we didn't know who was going to start smoking, what factors would precede it, but some of the factors would emerge over time, such as anxiety, depression, or even peer smoking, having peers who smoke. So that's what we learned from that. So this is an example of your cohort study where we have exposure versus non-exposure first. This is the structure of the study, right? We're trying to see which one ends up having the disease. Ideally for us, exposed would be more likely to have the disease than non-exposed. So that's actually what we're going to end up measuring. So for those of you who've had me in undergrad epi, this is review. Well, I'm actually, I think we did this. I can't remember if we did this or not. I know we did odds ratios, but I think we did this as well. Gosh, but if not, this is new to everybody then. When we look at the effect of exposure on an outcome, we can calculate incidence, right? Incidence means new cases. Incidence is also known as risk. So for instance, here we have exposed individuals and we have disease developing among the exposed and the disease not developing among the exposed. Incidence by definition is developing the disease among those who are exposed. So in this case, if we add together all the individuals within these 2 cells here and divide the total by the individuals, divide the number of new cases, right? People who develop the disease by the total of both those who do and those who do not develop the disease, we'd get the incidence, right? Incidence again, and risk are the same thing. So hopefully you understand why, because if the incidence is high, the risk is high, right? Relative risk is calculating the risk among the exposed divided by the risk among those who are not exposed. I mean, that's what we're mostly interested in. You could theoretically do it the other way around, but people are generally not as interested. They're more interested in the effects of exposure. So you're just taking the risk A divided by A plus B and then dividing that quotient by C divided by C plus D. All right. So here's an example. You want to calculate the relative risk of coronary heart disease for smokers versus non-smokers. And here are our data. We have smokers. There were 3,000 smokers and there were 5,000 non-smokers. And among the smokers, 84 developed CHD. So that's the acronym for coronary heart disease. And among non-smokers was 87. So if we do our division here, right, 84 divided by 3,000 and divide that by 87 over 2,000, we get our relative risk. In this case, it's 1.609. Now, just for your knowledge about interpreting these, because you do not need to know how to interpret them, a relative risk of 1 means the risk among the exposed is equal to the risk among those who are not exposed. So that's means there's no risk associated with exposure. Relative risk greater than 1 means that exposure really increases risk. a relative risk less than 1 means exposure is somehow protective. And, all of that stuff is very interesting. So in our examples, we'd say smoke. I mean, nobody wants, even though I do 3 decimal points, when you report things in a meeting, nobody's going to want to know 60.9%. They probably want to round this up to 61%. So I'd interpret this as that smokers are at 61% greater risk of CHD when compared to non-smokers, right? So you're not looking at the 1 value, you're looking what's above that. All estimates need confidence intervals. Estimates are just point estimates, but the true value will reside somewhere within that confidence interval. And we choose different types of confidence intervals, 95, 99, 90. I'll obviously tell you what kind you need. So again, the confidence interval is the interval in which we believe with some degree of confidence that the true population value resides. In any kind of statistics, we're always trying to estimate what's going on in the population from our sample, right? So, but we're not really sure if our 61% represents the true population relative risk. We need to find what it is. So a confidence interval is an estimate plus or minus a margin of error. Our margin of error, well, so what we do is we use something called the central limit theorem. That's not important. Next semester, if you're taking stats with me, you're going to see this stuff again. The central limit theorem notes that as a variable for every variable, for every type of distribution that's not normal, increasing the sample size will result in normality for the sampling distribution of the mean. Again, if you're not taking stats with me and whatever, you can just remember this, okay, for this class. So this margin of error is some z value. Z value is a standardized value. Alpha is the probability of a type 1 error. That I'm just showing you this right now. Again, in stats, you're going to have to know how to do this, multiplied by the standard error. So one of the problems we have with the relative risk and the odds ratio coming down the road here in a few minutes is that they're not normally distributed. In fact, if you think about it, relative risks cannot go below 1, right? We start at 1. They can go below 1, but they cannot go below 0. So they're, in a sense, they're skewed to the right. In fact, if we put 1 at the center, from 1 we can go to 1 to 0, but above 1 we can go up to 2, 3, 4, 5, 20. We can go, so they're highly skewed to the right. That's what I actually wanted to say. They're highly skewed to the right. Forget the stuff about 0. Yes, they can't go below 0, but that's irrelevant here. They're skewed far to the right, so they're definitely not normal. So we have to help them on their way towards normality, and we do that by taking a natural log transformation of the value, right? The natural log transformation, what that does is it quickens the effect of the central limit theorem in the convergence to normality. Okay, so if you're not really familiar with what a log is or what a power is and all that stuff, read through here. But essentially, I show you what E is Euler's number, and this is what we're doing here. So we're going to make this conversion here. So we're going to take the log of that number. So you'll see now that it's interesting that our equation has changed, right? So our equation now is the natural log of the estimate plus the standard, the margin of error. So we have to make that conversion. And it's going to even get more interesting than that in a second, okay? So the problem also, another issue that we have is that the variance is not normal either. Oh my gosh, right? And a non-normal variance is a problem. When we do any kind of estimation in statistics or any kind of statistics, we generally divide by the standard error. If the standard error is skewed in one way or another, that's problematic. Our general equation for the standard error is sigma divided by the square root of the sample size. But if our variance is skewed to one side or another, that's going to be problematic as well. A large variance would limit our ability to find something statistically significant. Small variance would increase the likelihood that something significant. So we're committing type 2 and type 1 errors respectively. If you don't know what that means, it's okay. Just follow what I'm doing here, okay? So we have to make some kind of a conversion, and we call this the delta method standard error. Again, if you don't want to care about that stuff, just think about plugging in the numbers here and you're good. So our delta method standard errors is 1 minus the probability. The probability is basically what we calculated when we calculated the risk, right? For P1 would be for whatever. Like in this case, we could say that's for the exposed, the probability of among the exposed, and then P2 is the probability among those who are not exposed, and 1 is the sample among the exposed, and 2 is the sample among those who are not exposed. So you can think of it that way. By the way, 1 minus P1 is just the complement of P1, right? And I think I talked about that a little bit the other day. If not, whenever we do probabilities, the complement is 1 minus the probability. All right, so we have to do all this stuff, and then we finally return back to our we want a confidence interval around that relative risk. That's all we're trying to do, but you can't just do it. You have to actually do all this manipulation in order to arrive here. So the confidence interval for our relative risk, well, this isn't all this stuff now is converted so that we can make it normal. So we have the natural log of the relative risk plus or minus this margin of error, right? And notice that that's in the exponent here. So this is e raised to this value here. Why? Because everything's in the natural log scale right now, and we can't report natural log to somebody. I mean, it would like drive them, they'd make their heads explode. They wouldn't know what they're doing, or so it would just drive people nuts. Okay, so we definitely don't want to do that. Okay, so we're gonna just give them a better report, hopefully, right? So we need to reconvert it back to its original scale. So we're going to put everything back in the log scale. So the inverse of taking the natural log is to exponentiate something, right? That's all we're doing. Okay, so this is what we had. This is basically showing you what the P1 and the P2 are. So this is the same thing that we did before in that earlier table, but it's just outlining everything for you here, okay? All right, let's go here. So here's an example. Again, we have 288 individuals exposed. Again, I suppose it could be smoking. 312 were not exposed. Out of the 288, 112 got CHD, and then 88 out of the non-exposed are CHD positive, and coronary heart disease. So let's go ahead and do the calculation. So the risk will be 112 out of those 288. So 112 divided by 288, that could be our P1 if you'd like to call it that. It's 0.389. The risk among those who are not exposed was 88 divided by 312, as there were 312 people, and 88 were CHD positive. That's a risk of 0.282. Notice here, though, we're just talking about the risk in terms of a proportion. We're not really doing it as, reporting it per 1,000, because we could do that, but that's not what we're interested in here. So we're keeping it in terms of these proportions here. So calculate the risk of the exposed versus the risk among the not exposed to get the relative risk, and we get a relative risk of 1.379, or we can round that up to 38, calculate the 95% confidence interval. So you just start plugging things in here, right? And again, I show you everything. If this makes no sense to you right now, don't worry about it. I actually have another video if you're interested about creating a confidence interval. It's not for this particular equation, but it explains all of this, what that means, the Z1 minus alpha over 2. All right, so we just plug things in. And I told you what the P1 was 0.389 and P2 is 0.282. The ends, we get our standard error. So that's our standard error, the margin of error. Now, for a 95% confidence interval, the Z value, the one that defines that boundary within the standard normal distribution, is plus or minus 1.96. So our margin of error would be 1.96 times our standard error, right? And we are the minus part's going to come in because we are subtracting it as well as adding it to our natural log relative risk. So we do all that in this exponent here, see? I took the natural log of our relative risk, and we got 0.321359. So the reason we have to exponentiate here is because you're not going to report this to somebody. What are you going to tell them? Well, the risk is the log the log risk is 0.321. They're going to say, what's a log? You know, am I a lumberjack or something like that? Or is this a Yule log? I mean, Christmas is coming up soon enough, right? So yeah, you don't want to do that. So we do everything in the exponent here. So we, for a moment, we ignore Euler's number here, right? Okay, and then we subtract the margin of error, 0.2287, from the natural log relative risk. We add it to the natural log relative risk. Then when we're done with all this, we end up exponentiating and we get 1.097 to 1.733. That's our 95%, in this case, 95% confidence interval. So how would I report the results? So our point estimate is 38%. Again, we rounded it up. So the risk among the exposed is 38% higher than the risk among those who are not exposed. The reality is that while that's our point estimate, it could actually be somewhere from 7.9% to 76% higher for those who are exposed versus not exposed. Okay, there's some limitations to the prospective cohort studies. It's not possible to randomly assign individuals to exposed and non-exposure groups. We are ethical human beings. We don't do that kind of stuff. Further, the time from exposure to disease development can be quite long. So you never, like, for instance, if you want to study the effect of smoking on lung cancer, I mean, you're talking about years and decades, right? So, you know, that's not really good because you might outlive funding, outlive researchers, et cetera. So retrospective cohort studies are an alternative. Here we have data that have already been collected. Problem is that they were collected for some reason, not necessarily for the reason of our study. Examples are adolescent health, AdHealth, or the PSID. Some of you are aware of the PSID, so it's a longitudinal cohort study. You don't have to collect data; it's cheaper, so that's an advantage. And as I mentioned, disadvantage. There are disadvantages as well. Like, we don't know what variables were added to that study, so they may not be the ones that we're interested in. We kind of have to live with what they have, and it's hard to control for confounding variables. So that's an issue. I know difficult to match participation. Matching participants is treating two participants if they're one. I mean, you probably can do it. Actually, there are some really cool methods for matching that are beyond the scope of this course, but you know, that's okay. Some people use medical records as well. People who are hospitalized, there's a lot of great records for them on a variety of things, but those records are not necessarily going to be complete. And then to generalize from a hospitalized population to a non-hospitalized population isn't ideal because there's selection bias. Selection bias means that people who are hospitalized are different than those who are not. So people sort of self-select based on whatever bad experiences they have to be in the hospital. Another type of longitudinal study is the case control study. The case control study is a kind of an interesting type of longitudinal study because it's not really longitudinal. It's, in a sense, it's cross-sectional. Because you have data on individuals and then you look backwards in time based on the responses they give you. So in a weird way, it is cross-sectional more than longitudinal, but we treat it longitudinally. Case control studies are ideal when we're looking at individuals who have some kind of a disease, and we want to compare people who have the disease to people who don't have the disease on their odds of exposure. Like, so when we're trying to ascertain exposure, a good example was in the history of smoking, how one identified cigarette smoking as the risk factor for lung cancer was through looking at people who had lung cancer and who didn't, and realizing that the majority of people who had lung cancer smoked. So there was an ability to look backwards in time. Okay, so you want to identify exposure, but because we're going backwards, we cannot use relative risk here. So relative risk means new cases, and these individuals are already cases. So you can't use that. It's just logic there. So we calculate the odds ratio instead. So you can use the odds ratio both in cohort studies and in case control studies. Relative risk can only be used in cohort studies. You just keep that in mind. So odds ratio is more robust. But then again, sometimes people like to talk about risk rather than odds. And odds, just for for your knowledge, in probability, odds is the probability of success divided by probability of failure. Success is whatever you're looking at. Do not treat this qualitatively, because if we're looking at lung cancer, we're not saying, success, somebody has lung cancer. But that's just a probability language. Success is what we're looking for versus failure. Just like the relative risk and odds ratio is a ratio of odds, right? Odds among those, odds of exposure among those who have the disease divided by the odds of exposure among those who do not have the disease. Okay, so that shouldn't be anything really horrifically difficult to calculate. So actually, I think we're using the same example here, except for now we're looking at odds of exposure among cases, CHD cases. So we have these CHD cases and we have controls, and when we want to see the odds of being exposed to a certain risk factor. So we just need to calculate the odds of exposure among each group. Now, odds relate to probabilities. So in this case, I am not going to use probabilities. I'm just going to use the raw data here. So I mean, if I wanted to do probabilities, I would do 112 divided by 600 divided by, well, actually, if I'm doing it among the cases, it would be 112 divided by 200 divided by 88 divided by 200 to get the odds, but I don't need to do that. And if you just work that out, the 200 just cancels out, so you don't really need to do that. So I'm going to calculate 112 divided by 88 because it's exposed versus not exposed, success divided by failure. So to get the odds among the odds of exposure among the cases, it's 112 divided by 88. That's 1.273. Odds among the controls, and we call the controls individuals who do not have the disease. Okay, individuals who do not have the disease. And here would be 176 divided by 224. So here we have the two different quotients, right? The numerator and the denominator. So whenever you take something from the denominator and bring it to the numerator or quotient, you flip it, right? So basically we get this telltale, or I shouldn't say telltale, but this quintessential equation for an odds ratio. You go 112 times 224 divided by 88 times 176. And what I mean by quintessential here is you get this crossing, right? 112 times 224 divided by 176 times 88, right? So that always happens whenever we have an odds ratio. So in this case, our odds ratio is 1.62. The same rules apply as they did to the relative risk. Values above 1 means there's an increased odds. Values below 1 would mean there's a decrease in the odds, right? Calculate the 95% confidence interval. So we're sticking with 95% because we're in this epi class. This is in stats. We're going to stick with 95. You're never going to encounter from me in an exam anything but 95. When we get to statistics, you will. So we already know from the last equation that z1 minus alpha over 2 is going to be 1.96. That's going to be the same here. So we have to make the same adjustments here to normality for the exact same reasons. There's a skew, right, from surrounding 1, right? Again, 1, you can go way above 1, but you can only go from 1 to 0. So it's heavily skewed to the right. So basically, we're doing exactly the same thing here. So we have to take the natural log of the odds ratio, right, plus or minus the margin of error. And then to get the odds ratio, we're going to exponentiate. So everything's exactly the same. The only difference is now we have this standard error. It looks a little bit different. The A, B, C, and D are the different cells. Oh, just for your information, when you do odds ratios, it's a 2 by 2. So, I mean, sometimes you could have more than 2 groups. Like, say, if I have high exposure, moderate exposure versus controls, and then I have, something like that, right? Disease versus not a disease. So you can have more than a 2 by 2 table, but for calculating odds ratios, you do it in 2 by 2. So even if you have larger tables, you have to convert it to a 2 by 2. But within that 2 by 2, there'll be 4 different cells, and the standard error is 1 divided by whatever cell A is plus 1 divided by cell B plus 1 divided by cell C plus 1 divided by cell D and take the square root of that. And I have a proof of that if you're interested. That was one of my favorite things that it vexed me. I can't stand things that look like this that don't make sense when you just look at them. So I went and did a proof of that. That was fun for me to do. So that's our delta method standard error. So then we use that in calculating the margin of error, and we take the natural log of our odds ratio. The natural log of 1.62 is 0.48. And again, we can't communicate log odds to somebody because that sounds really weird and nobody will know what it means. So we have to exponentiate this bad boy to get back to something that we're used to. So when we do this transform, well, let's just look at this right here. Everything's done in the exponent again. So I use the same process as I did for the relative risk. Then I bring it back down to the odds ratio term, to the scale, right? So our 95% confidence interval is 1.15 to 2.80, right? 2.280. So how do we interpret this? Cases were, well, our odds ratio is 1.62. Cases were 62% more likely to be exposed than controls. You provide the odds ratio and the 95% confidence interval. That means that the true odds ratio is somewhere between 1.15 and 2.280. What if we were looking at controls, odds ratio for controls versus cases? Well, you can just take the reciprocal of that. 1 divided by 1.62 is 0.612. How would I interpret that then? We could say that controls are, well, 1 minus 0.612, 39% less likely to have been exposed in comparison to cases. Or if you want, you can just read it directly. Controls are 61% as likely to have been exposed in comparison to cases. Get to know that because you need to interpret these for people, for the average Joe, as they say. There are limitations to case control studies. Individuals with diseases tend to remember, or they tend to remember exposure more than those who do not have it. I mean, think about it. If you had, well, I'm sure most people had COVID. If you had COVID, you probably thought about, where did I get this from? So you think more about it than somebody who doesn't have a disease. Yeah, that's going to have an impact on artificially increasing the exposure rate in cases compared to controls. If the controls don't pay much attention to the potential exposure. Matching helps control for confounding variables. Matching is when you treat the cases as the same as the controls. So then they become basically the same individual, right? There's ways to do matching. There's something called propensity matching that I really like, where you actually, once you have the cases of control, you create them as the dependent variable, right? In a logistic regression, and then you regress them on a whole bunch of predictors, and then each person gets a propensity score based on those predictors, and then you match. It's pretty cool. Just one last thing I want to talk about is create cross-section. Oh, by the way, the way we would calculate the odds ratio would be different if we use cases. We use matching, just to let you know that. It's not the same as what we're doing here in this case. Cross-sectional studies, we have, so cross-sectional studies is just a study where you collect data at one time point and you make some kind of a model to explain whatever you're trying to explain. Really easy to conduct. It doesn't take a lot of time. I mean, again, you do all the data collection and one time point. It's very cost effective. Problem is there's an inability to judge precedence because you don't know if the exposure occurred before the outcome. And there's also something known as a cohort effect. So you have people of different ages within your cohort, right? I mean, within your data. And each of those individuals comes from a different cohort. People in different cohorts have different experiences. So if you're doing a study, say, on PTSD, and some people lived through 9/11 and other people didn't, you might have different effects there. And it's hard to deal with that when you're, doing a cross-sectional study to eliminate that. There's ways to control for stuff, but that's beyond the scope of this course. That's it, my friends. Have a wonderful day.